Hello and welcome to the training for True Load for Ansys Workbench. This is Tim Hunter. I'm president of Wolfstar Technologies. The products from Wolfstar Technologies for Ansys are True Load, which is our flagship product, and this turns components into load transducers. And we do this by placing strain gauges located on a component being driven by the FEA model and setting that up to be sensitive to certain unit load cases in the FEA model. So we extract a correlation matrix from the FEA model that maps to strain response. Then you as a customer will place the strain gauges on the physical part, measure the strains and the testing conditions, and then we'll take those strains then and back calculate the loads by multiplying by this correlation matrix. So True Load basically will turn any component into a load transducer. And then we also have True-QSE. QSE stands for quasi-static events. So quasi-static events are basically load cases from the FEA model that are linearly superimposed by user-defined functions. And this by itself is great, but what happens is that when you run True Load will basically generate time histories of loading that corresponds to the load functions in the load cases in your FEA model. And those loading functions came from your time histories of strain. So basically, True Load is going to generate time histories of loading functions that map to unit load cases in your FEA model. And True-QSE is essentially then a post-processor that lets you post-process the model very easily and very conveniently. And True-QSE comes bundled with True Load when you buy True Load. You can buy True-QSE separately, but you could also just buy True Load and True-QSE comes bundled. And then at any point in time, if you want to do fatigue, we've got interfaces to the major FEA-based fatigue codes, and so you can export your results in True Load and True-QSE to your FEA-based fatigue codes to very easily do accurate strain correlated loading going into your FEA-based fatigue. So this is a great tool to help you do fatigue, but you don't need to have durability packages to use True Load because True Load is essentially calculating the loads on your product, and you can use those loads for any number of design activities, one of which is fatigue. But you can use it to understand displacements, to understand flexibility, to understand customer profiling for your product. So this is a very important tool in and of itself, but we also then help you drive FEA-based fatigue if that's what you want to do. So here's the syllabus for our classes here. So we're going to start off with the True Load theory. That's what this presentation is going to be about. And then I need to orient you to the TFU manager. TFU manager is our function manager because we're generating lots of functions. So we've got an open source function manager that comes with our software, and we're going to spend a little bit of time to orient you to the TFU manager. Then we'll go into a cantilever beam and do some basic theory around the cantilever beam and set up a full example around a cantilever beam. And then we'll get into the question about how many gauges. And then I've got a little bit more complex example with a headlamp for a motorcycle. And then our final example will be a Baja car that was done with the SAE team at the local university. So these are the exercises for the standard training, and then at the end we can have advanced techniques and get into some customer projects examples if we were on site. Okay, so this is the overall syllabus. For sure, we will go through the cantilever beam and the headlamp in these set of recorded trainings. So a little bit about, so we're going to go into the True Load problem statement and theory. This is going to be the bulk of this presentation today. So True Load is all about understanding the loading on your complex products. So if you've got products that look like any of these here, from construction equipment to bicycles to motorcycles, automobiles, aerospace, wind turbines, we have got customers in all of these segments, and we help our customers understand the loading on their products to drive better product development. So a little bit about historical concerns with loading. So any analysis you do, you've got great CAD geometry, you've got great meshing tools, you've got great material models, you've got great solvers, and the biggest unknown in the whole process is when you go to take your FEA model and submit it for a solve, it's basically a guess on your part oftentimes. So if you're guessing at the load cases, you're basically guessing at the solutions. And in the US, we've got this term called GIGO, garbage in, garbage out. So if you're just guessing at the load cases, you're guessing at the results. So you're going to spend many times going through many iteration cycles because you don't fully understand the loading, and you're going to go through the design, the analyze, design, build, test cycles several times through. So traditional load measurement can be expensive. So traditional load measurement will use tools like you see on the screen here. These are standard load transducers, and these are fine, but every time you introduce the load transducers into your system, you've got to cut away part of your system, introduce the load transducer, and then reinforce it. So now you've changed the masses, you've changed the load paths, you're measuring something, it may or may not be the actual load, and then worst case now, you're going to take that back to the FEA analyst, and the FEA analyst has got his model set up in the as designed condition and not in the as tested condition. So now the FEA analyst has got to rework his FEA model to look like the test product in order to use your loads. So this isn't a perfect world, but this is what traditionally you need to do before true load. Another technique people like to use is strain measurement. So typically an FEA analyst will look at the FEA model of their components, and they'll look at the stress and strain results, and they'll come up with a number of strain gauges. They'll talk to their colleagues and come up with a couple of more strain gauge locations. They'll collect all the strain data, and when they get the strain data back and they look at their FEA model, they just can't understand the connection between the test data and the FEA model. And so they'll spend days, if not weeks, trying to get one or two channels of data to match up at one or two points in time, and then they'll use that for the design load cases. And the next time they get to the field and they go in and they do the testing, and they find they've missed something, and they're back doing it all over again. This is just typical to what happens, and we see this all the time. So what's wrong? Well, your company's investing in great analysts like you, world-class FEA software, investing in the right equipment to do testing, and they're investing in great tools to do FEA-based durability. So they're doing all of the right things, but they're not getting the right answers. So what's wrong? Well, you've just got too many variables to manage. The gauge locations, the load cases, and the quantity of data. So when you think of these data streams that you get from the field, they could be 500,000 data points. And at each point in time, at these 500,000 data points, you'll have a unique loading recipe that drives the strain at that point in time. And that is just impossible for you to perform manually. So you're just left spinning your wheels, and you're just in no position to be able to perform this using manual means. So the solution is true load. True load, quite simply, is in situ load measurement. So we're turning complex components into multi-channel load cells, and we do this by leveraging the FEA model and the test data to work together. It works with all FEA codes, and if you've got Abacus CAE or Ansys Workbench, we've got plugins that make it even easier to use. And at the end of the day, you get optimal placement of strain gauges, and we support all the major FEA durability codes. So here's a workflow for true load. You're going to start off with an FEA model like normal, but rather than coming in with just a single unit load case that's a complex loading on it, I'm going to have you take your loading and break it into a series of component loads. So an X component of load, a Y component of load, a Z component of load. maybe a pressure load, maybe a thermal load, maybe an inertial load. But the mindset that you need to have with these unit load cases, that if you could mix those together, could you approximate the operating environment of your part? So this is you designing the unit load cases for your model that you're going to use to then approximate the time histories of loading conditions if you could mix these together. Solve that FEA model with all those unit load cases, and then you go into true load pretest. And in pretest then, we're going to then take a look at the strain results from all those unit load cases and then come up with the optimal strain gauge placements. And then once we've got the strain gauges laid, we have tools that allows you to reposition and reorient the gauges so that they're nice locations for the test engineers to lay the gauges. But at the end of the day with pretest, we're going to have two things. We're going to have the strain gauge placements on the model, and then we're going to store a correlation matrix that relates the strain response at these strain gauges to each of the unit load cases on your FEA model. Once you're done in pretest then, we go into the physical world and we lay the strain gauges on the physical parts in the lab, and then you could test these products in the lab, or you could take them to the field and look and record the strain data in the operating environments. But at the end of the day, we're going to come out of the strain measurement task with time histories of strain data, and we bring that into post-test. And then post-test, we'll take the measured strain histories from test and multiply them by the correlation matrix from pretest, and we'll generate time histories of loading functions. And these will be strain correlated time histories. And then you can bring those time histories into your FEA analysis package and use those time histories of loads in your FEA analysis package and do the FEA calculations with your traditional tool with using traditional techniques. And that's fine. But I highly recommend that you use True-QSE because it'll automatically organize all the unit load cases and all the loading functions and very efficiently will produce all the strain results and all the results that you want to look at. So True-QSE is a very efficient tool for doing it, but you don't have to use True-QSE. You can use your traditional FEA tool. And then at the end of the day, if you want to do FEA-based fatigue, now that you've got strain correlated loading functions, you can use that then to drive the loading time histories into your analysis, and you can do the FEA-based fatigue. So this is what you can do, and you can use any major FEA-based fatigue code to do that. So you look at this complex flowchart here, and really the top four blocks are you turning your part into a load transducer. So you're turning your component into a load transducer with the top four blocks. And the bottom flowchart is you doing design and optimization once you've got the loading functions. So when you look at this, you might do the top flowchart, the top four blocks once, and then you take those loading functions down into the design and optimization loop, and you might go through that 30 or 40 times as you optimize your product. And then the next time you get into hardware and you've got a new level of prototype, you might do the top four blocks one more time on your refined design to see if your loads have changed and if you need to refine your loading. So this is a typical process that all of our customers do. So this is all based on linear systems and loads. So linear systems is where loads are proportional to displacements, displacements are proportional to strains, strains are proportional to loads. It's a linear system. Now I realize everything is nonlinear, but we're turning our part into a load transducer. So we're going to target the nominal locations on the part, and we're going to stay away from strain concentrations due to welds, due to bolted joints, due to slop, due to elastomers, due to contact. We're going to be just out in the nominal regimes on the part, and we're going to lay the strain gauges in these nominal locations. We need the strain response to remain linear. Okay? The loading can be as nonlinear as anything. The loading could be sinusoidal, it could be ramp loading, it could be impact loading. That doesn't matter. I just need the strain response to be linear. So you take a look at this, and you can basically take this diagram and turn it into a couple of equations. So the right-hand side, well, that's F equals Kx. That's Hooke's law. So if Hooke's law applies to your structure, then its corollary, the left-hand side of the triangle, which is strain times a correlation matrix is equal to load, has got to apply. And this is what true load is using. True load is basically taking the strain corollary of Hooke's law and calculating forces as being strains from test times a correlation matrix from FEA. Okay, let's take a look at this a little deeper here. So here's our equation. Strain times a correlation matrix is equal to load. And in this example here, we've got 3 unit load cases in our FEA model, and we've got 4 strain gauges laid on the FEA model. So the columns of the strain matrix represent uniaxial strain gauges. And in this case, we've got 4 uniaxial strain gauges and 3 unit load cases on our FEA model. So let's go through this row by row and let's see what this does. So here we turn on load case number 1 and turn load cases 2 and 3 off. And then you can see at the strain gauges 1 through 4 here, we're going to get a strain response, and we're going to record that strain response. Now let's go in and turn on load case number 2. So we've got load case 2 turned on, load cases 1 and 3 turned off. And then at those same 4 strain gauges, we write down the strains. And now the strain responses at these 4 strain gauges are going to be different than they were for load case number 1. We're essentially getting a strain signature for each of these load cases. And then we do that again for load case number 3. So we got load case 3 turned on, load cases 1 and 2 turned off, and now we get another unique strain signature for load case 3. So now we've got 3 unique strain signatures for 3 unique load cases. This is a well-behaved linear system. So I've talked a lot about loads here, but let me just talk about that a little bit more. So the loads could be anything. They can be point loads, they can be moments, they can be pressure loads, they could be thermal loads, they could be unit displacements. They could actually even be mode shapes. So we could go in and we could calculate the mode shapes on a structure and have true load place the strain gauges on the structure based on mode shapes. And then if you collected the strain data based off those mode shapes, then true load would directly back calculate the modal participation functions of those mode shapes. So very easily you can go in and understand a complex dynamic loading going on in your structure. And we can take that another step further. So if we had a cover and we solve that cover for its normal modes, and then we're the cover attached to the structure, if we put unit displacements, XYZ unit displacements at the attachment locations, and we laid strain gauges with true load based on all of that, so the unit displacements plus the mode shapes, and we collected the strain data and brought it back through true load would be essentially doing a Craig-Bampton analysis with that, where we get the ground flexibility going into the structure through the unit displacements and the harmonic response with the mode shapes. So it's an extremely powerful way to understand the dynamics of your structures. Okay, so we've got this nice equation here, strain times C is equal to F. So the only thing we haven't talked about here is C. So how do we find C? So if I take a look at the F matrix, and if I call turning a load on a 1 and turning a load off a 0, then the F matrix can become identity matrix, and then I can do a pseudo inverse. So basically I take strain times C is equal to I, pre-multiplied by strain transpose, pre-multiplied by strain transpose, strain inverse, and we get C is equal to strain transpose, strain inverse, strain transpose. And that's what we pull out of the FEA model. Okay? So we've got a nice equation here for C, and now we've got to figure out where to lay strain gauges. So we've got infinite number of places to lay strain gauges, so which ones are best? So what we recognize here is that there's an inverse in this relationship here. And inverses can be very poorly behaved, but that's not what we want. We want a well-behaved inverse. And so what we're going to do is we're going to recognize that the inverse of a matrix is defined by the cofactor of the matrix divided by the determinant. And we're going to take the thing in the bottom, the determinant, and maximize that. That's going to be our objective function for finding gauges. And we do this hunt for these strain gauges with the Galil-Kiefer de-optimal search approach. It's borrowed from design of experiments, and it's a very efficient way to go through a very large number of strain gauges and elements to decide which is the right strain gauge locations. So this is the algorithm for finding strain gauges on the part. An interesting fact here is that when you satisfy the determinant of strain transpose strain is equal to maximum, you've basically identified the maximum, you've identified the main load pass in the structure. So in and of itself, it's a very informative tool to understand where the loads are flowing on your structure. Okay, I'm going to show you the TrueLoad workflow with a little graphics behind it. So here's a headlamp example that we're going to go through in the training exercises. So the analyst, when he looks at this headlamp, says, this headlamp is basically attached to the front of a motorcycle. It's getting excitation from the front suspension, from the handlebars, from the frame, from the engine vibrations. The analyst chooses to model this problem as a base excitation model. And so what he's going to do is basically restrain the headlamp to ground at the bolt locations and apply unit acceleration forces in the X, Y, and Z directions. So that's how he's choosing to model this. So the loading and boundary conditions look like this: restrain it to ground, and X, Y, and Z loading, and acceleration loading. And then he goes in and launches the pre-test application. So in pre-test, it's going to load up his 3-unit load cases automatically. And then once he's got his load cases loaded in, he's going to select a subset of the model for placing strain gauges. So he's choosing areas in the middle of the headlamp bucket and in the middle of the legs here. And he's staying away from boundary conditions, and he's staying away from where parts hook up to other parts. So he's choosing to have these nominal areas as being his candidate strain gauge locations. And then he tells TrueLoad that he wants 6 strain gauges and tells TrueLoad to go find those strain gauges. And TrueLoad then draws up the strain gauges on the screen, indicating the position and orientation of each uniaxial gauge with a line and labeling it up here with a nice little note. So once he's happy with the strain gauge placements, then goes in then and goes to the lab and places the strain gauges on the physical part and measures the strains on the physical part, and he collects these time histories of strains. Now the whole point then is we're going to take these measured strains then and turn them into time histories of loading functions, and we're going to do that with the post-test software. And in post-test, we're going to load in the pre-test file, which has got the C matrix in it. We're going to load in the strain data file from test, and then we push this button over here to generate the loads. And it's that simple. Now there's things on here to map and drop channels, to plot data, but really at the end of the day, it's bringing in the C matrix from pre-test, we're bringing in the strain data from test, and pushing the button. And then it generates these loads, and then post-test will also generate for us a QSE file. So here's the QSE file then, which has got the 3-unit load cases and the 3 time histories of loading that was created from the strain data. And so this is great now. We can then go in and probe any node, any element that we want to get XY plots of any data component of results that we'd like. We can go in and generate an operating deflection shape, or we could go off and do FEA-based fatigue if we'd like. So these are all things that we can do with TrueLoad to go in and understand our loading. Now, the whole point of TrueLoad, though, is to understand the loads and then do redesign. So what we can do now is we can go back to our FEA model, and we can go in here and we can change the FEA model. So we can poke holes in it, we can thicken things up, we can do whatever we like. And the requirement we're going to make now with TrueLoad is that you only solve it for the first 3-unit load cases. You only solve your FEA model using the 3-unit load cases, and then we just come back to QSE, and we just have QSE point to your new set of FEA results. And that's all we do. We just change out the FEA results, and then it will linearly superimpose the data together based on these loading functions that we've calculated. So this is a very, very efficient way to understand very complex loading on your part in the redesign mode. Okay. So I've got a short video here giving a very high-level overview of the TrueLoad Workbench interface, so we can see how it works in Workbench. So here we go. I'm going to just play that back. So we've got a very complex Workbench model here, and I've just added in the pre-test module in and updating it, and we're going to just launch pre-test, and it's going to bring in this structure in that we can go in and place strain gauges on. And so here's the Pretest module, we just load in all the unit load cases once it comes up. Here's an isometric view so you can see what we've got. And load in the unit load cases. And then through a series of work, we've gone in and selected elements and told TrueLoad to lay 30 strain gauges here to be sensitive to our 15 unit load cases. Okay, so very easy, very straightforward task to go in and lay those gauges and get done. And then once we're back to the workbench, we can go in and add a QSE event, and we can also add in post-test. So we're going to take post-test then, and post-test then is going to be used then to take some measured strain data that we've got and turn it into loading functions. So we just go in and launch the post-test module. And all we've got to do now is bring in the test data, plot up the test data if we'd like. And then we just tell TrueLoad then to calculate the loading functions, and it goes through and it does all the calculations, generates this a nice HTML report. And that HTML report has got the gauges listed. It's got our desktop environment. And then we're going to show you in a second here the overall strain correlation. And you can see on this cross plot here, the horizontal axis is measured strain, vertical axis is simulated strain. It's great. And then if you look at the correlation table, we've got an average of 0.78% strain error in strain. So excellent, excellent correlation here. Okay, so here's an experimental test case from Harley-Davidson when they were first benchmarking the software. What they did is they went in and they designed this little test fixture because they wanted to have a very simple geometry to make sure everything was working right and not have to worry about geometric issues. So they wanted the strain gauges placed by TrueLoad to tell them the loads on the structure. And what they did was they put an independent load measuring system on here of a large mass and 3 accelerometers to be their independent measure of load. And so you can see what they've got is they've got an FEA model on the left here. TrueLoad is showing them where to place strain gauges. On the right, you can see close-ups of the strain gauge placements in the virtual and the physical setting. And they placed it on the back of a motorcycle. They loaded up all the strain gauges. They loaded up the accelerometers and they took it off to the test tracks. So here's the results. So here's their calculated forces. They measured forces as being mass times acceleration, and here's the X, Y, and Z forces. And then superimposed in blue on all three of these plots are the forces from TrueLoad as being strains from test times a correlation matrix from FEA. And you can see that we're very, very close here. And when you do the RMS error calculation, we're within 6% on the force calculation here. So the worst error is 6% RMS error in load calculation. So that's not bad for just pushing a button. Now these next plots are standard plots from TrueLoad. So what you're seeing here is we had 6 strain gauges laid on this part. So you're seeing 6 time histories of strain. And then TrueLoad takes the measured strain times correlation matrix to calculate the loads. And then we go in and take those calculated loads and go back in the FEA model and we pull out the time histories of strain at the strain gauge locations and plot those on top. And so the green curves are measured strain, the blue curves are simulated strain, and you look at them and they are line on line, okay? And if you looked at the percent RMS error, the worst percent RMS error is 0.1 RMS error, 0.1% RMS error here. And this is just an excellent correlation that you get, again, just by pretty much clicking one button. Okay, so just a summary here. With TrueLoad, you're going to get optimal strain gauge placements, you're going to get unprecedented strain correlation, and you get strain correlated load histories. That's so important to give you tools for doing redesign. And TrueLoad is going to reduce your test and analysis time because you're going to have correlated loads, and your test cost now is only the cost of strain gauges. So strain gauges cost about $10 a piece. They take maybe a half an hour to install. So this is a very, very inexpensive testing thing. We don't have to modify your parts at all. We just put strain gauges on the parts as they are. And then you get the proper knowledge. And what you'll see is that you'll end up eliminating iteration cycles, because now that you understand your loading, you as an analyst now are going to make better design decisions, and you're going to be eliminate whole iteration cycles, and it's going to save you huge amounts of time and money just by doing that. Okay, so this is the end of the first part of the lecture. I'm going to pause this, and then the next lecture is we're going to go into TFU Manager.